Okay, now it's being recorded. Boy, I blew that. Thanks, Gary. So anyway, yeah, now it's being recorded. Um, so anyway, you'll be able to listen to, listen to the vid or watch and listen to the videos, or look at the, look at the transcripts. So anyway, it's right there. Now let's take a quick look at sapling. Um, don't recall if I made any changes on you guys. Yeah, I think I did. So the thermochemistry topic introduction and homework is due in 2 days from now. But we finished it up on Friday, so you guys should be good on doing this. If it's causing an issue for somebody, let me know though. And then for the new chapter that we're going to be starting today, chapter 6, quantum theory, electronic structure, periodic properties of elements, those are going to be due on April 11 and 12. We can adjust if need be. We still have some time in the semester to do that. So anyway, just wanted to bring that to your attention. But anyway, this would be the due dates right as they stand right now. Okay, I think that's it. Okay, so I'm going to stop sharing my desktop. And one more time, has anybody got a question about anything? Raise your hand, or you can chat it. Okay, looks like we're doing all right there. So I will get right into the PowerPoint here, and we'll get going. You know, Gary, it's kind of funny. I have a note here right next to my laptop that says "Start recording." You know, that doesn't seem to get the job done. Anyhow, hopefully it. I'll get more into the habit. Okay, I'm not getting to the right place. Oh, okay, that's what I need. So the new chapter is going to be chapter 6, electronic structure, periodic properties of the elements. So here you go. Chapter 6, electronic structure, periodic properties of the elements. So what we're going to start out with is looking at wave properties. And this is important because an electron, oops, I got to get the marker going. Electrons they have what's called a dual nature, in that they can be a particle or they can be a wave. So with a particle, you know, they've got a particular location, but that location's changing all the time. And when we think about them as a wave, uh, then, you know, it's going to be behaving a lot like light. So there's a similarity between a electron and a photon of light. So with waves, we got a couple different properties that are going to be relevant. The first thing is going to be our wavelength. Sorry, even with this tablet thing, it's still not really great to write on the screen. But anyway, first thing is wavelength. That's the distance between two adjacent peaks. You can text at the top. Oh yeah, that's true. Yeah, that's right. I can type on it. Thank you. Sort of forgot that. Okay, so wavelength is thank you, Carla. Uh, so wavelength is the distance between two adjacent peaks. And then the next property, I'll go ahead and do the texting part then. Um, is going to be the cycles per second. The only problem with this texting thing is that it's just, oh, okay. It's just really small. Here we go, that's better. So cycles per second, or the other way you can do this, yeah, Gary, you're right. You could take the bottom or the top of the peak. It really doesn't matter, you know, but that's what you're comparing to each other. So this cycles per second is equivalent to saying frequency. I wish there was a way you could set the type to be bigger, because this is not too good. I wish it would also fix my spelling. But anyway, so with wavelength, again, that's the distance between the two peaks. And frequency has to do with if you were observing the peaks. So this would be like standing on the beach, and you're watching these waves go by. How many waves are going to go by in a second? So this first picture, if 4 waves go by in a second, we call that 4 hertz, 4 cycles per second. If you have 8, that's 8 hertz. If you see 16 go by, that's 16 hertz. And frequency is going to have a symbol that looks like this, looks like a V that's got a little squiggle on the top. And then wavelength is going to have a symbol that looks like an upside down Y. Boy, I didn't do too good on that. Try it one more time. I can't type those kind of symbols very easily. And then the third property, not quite so important to what we're going to be doing, and that is how high is the peak from the middle point. So, and that's called the amplitude. So they actually have that word on the slide. That's the amplitude. But the first two, wavelength and frequency, it's what's going to be more important to us. So going to this next chart, what we're looking at here is different source of radiation. So we're going from low energy like AM radio, ultrasound, microwaves, your Wi-Fi connection, stuff like that, cell phone. That's going to be longer wavelength, and it's also going to be a lower energy, and it's going to be lower frequency. And then we get on the opposite side here, we got things like a PET scan, X-rays, cosmic rays, and all that stuff. Those waves are shorter, and since they're shorter, their frequency is going to be higher, and also associated with that is going to be higher energy. So from this slide, what I want you guys to get is the stuff that's in the blue here. That if it's high energy, it's also going to be high frequency, and it's also going to be short wavelength. Where on the other side, if it's a lower energy, it's going to be a lower frequency, and the wavelength is going to be longer. Okay? And this picture right here for visible light, unfortunately, is incorrect. The blue should be over on the left and the red should be over on the right. So they messed up when they did this illustration. So this is actually not correct. It should be flipped for visible light. Okay, now we're going to take this And we're going to finally get around to some chemistry here in just a second, but we haven't quite got there yet. This is mostly up to this point physics. So there were several experiments done looking at electrons and the particle nature of electrons, but also the wave nature of electrons. And we're not going to spend time on that because it's not going to change things up for us very much. So we'll just not have, we just don't really have time to do it. But one experiment that I do want us to focus on is the photoelectric effect. So what you have in this, well, in all these cases across the bottom here, you have a piece of metal. And the metal is inside of a vacuum tube. So they have taken out all the air. So it's a vacuum. And the reason why they would do that is so any particles that are going to be present, those are not going to be bouncing off of anything else inside the experiment. So this is done inside of a vacuum. So in the first experiment, that's this one over here. Oops, I think I got to. Okay. So for our first experiment, the wavelength is 700 nanometers. So that's a very short distance. And associated with that wavelength is a color. So you can see that for this first one, it's red, obviously. And when that light impacts the metal here, wow, I don't know why it did that. Oh, I must have hit the showing an object. Anyway, when it impacts right here, it says no electrons were ejected. Then they repeated the same experiment, except they changed the wavelength, which means they basically changed what color of light they're using. So this time around, we're going to have green light. And in this case, when we use the green light, when the light, excuse me, there we go. Okay, when the light struck the metal, then it ejected an electron, and they were able to observe the electron. And what they were able to do up here was actually get the frequency of it, and they were really observing that like a velocity. So 2.96 times 10 to the 5th meters per second. So in the third experiment over here, they went even shorter wavelength. So as we're going across here, notice that we're going from a long wavelength to a shorter wavelength. But like we said before, that a long wavelength is associated with a low energy. So when we're going across here, when we go to a shorter wavelength, we're going to actually have a higher energy light. So this last one over here, color's purple. Now this light stuff, the colors and everything's going to come back a little bit later, so that's why I'm doing those. P-U-R-P, oh, okay. Whoops. I don't think it's going to let me type in. No, it's not. Oh, well, anyway. Okay, just imagine it says purple. And so now when we did that, it ejected an electron. The electron has a higher velocity or a higher energy, higher kinetic energy. Now the main thing here is what this is pointing out to is that out of the 3 experiments, only 2 of them were successful at ejecting an electron. But in the first case, it didn't. And what this is saying is that there is only certain energies of light or certain colors of light that can eject an electron, and then the electron is going to have a specific energy. So this is eventually we're eventually going to get into the elements, and we're going to see how that works. Now we have a formula in here that the energy is associated to the frequency. You got energy equals, and then there's a constant, it's called the Planck's constant, H, and then the little V-like symbol, which is, representing frequency. So the higher the frequency, the higher the energy is going to be. Okay, let's move to our next slide. So now we can use what we saw on the previous slide to look at these 2 sorts of experiments. In the first case, up here, we have just an ordinary light bulb. So it's an incandescent light bulb, and so the light is more or less white. So we've got the colors present. If we then shoot that light through a prism where it's separating the different colors, so we're, purple at the top, red at the bottom. If we were to display that across a surface, we would see all those different colors present. Now, on the other hand, if instead of having an incandescent bulb, let's say we have a bulb that only has one particular element in it. Let me get the text going here. So now you only have one element in that tube. So because of that, you're only going to get one color of light, say green light. So that when that impacts the prism, you're only going to get just this single color. And that single color, if we look over here on the right, would show up as a single, let me change the color so you'll be able to get on here. It'll show up as just a single line. Now, I realize we're seeing more than a single line here, and we'll get into that a little bit later as to why there's more lines present. But that's essentially the idea that we're looking at here. So with continuous spectrum, that's what the white light is here. With a line spectrum, that's going to be these ones below here. Okay? So now we're going to relate this whole thing, color of the light, and whether you even see light, to the energy levels of an atom, and then we're eventually going to end up with the orbitals that the electrons occupy. Now, again, what we're seeing here is that if you consider the wavelength, which is also really the color of the light, that if the wavelength is shorter, well, this is actually, yeah, that's right. If the wavelength is shorter, then the energy is lower. And then if the wavelength is, I think I'm doing it backwards. Oh, yeah, that's the way it's supposed to be. The wavelength is longer, the energy is lower. And if the wavelength is shorter, the energy is higher. or if we were doing this in terms of a color, the longest wavelength light's going to be red, and then the shorter is going to be blue, pretty much. Okay, so now what we're getting over here to the right of that is this is for a hydrogen atom, and when we apply energy, it's going to elevate an electron into only certain levels. And then when the electron falls back down, so if it falls from that level, it's going to produce a certain color of light. And that is the color that you're seeing in the line in the previous slide in the spectrum. Now, it can fall all the way from where it is to the bottom level, or if you're at a higher one, say this next one higher, it can fall to the next level, or it could fall all the way to the bottom again. So now you can get two more colors. So that's why on the previous slide that we're not just seeing a single line for a particular element, you're seeing different lines. But notice that there's a lot of color that is not present, like in this case here, you're missing all this light in between because that does not correspond to any possible orbital or possible energy level. So now taking this a little bit further now, we get to this picture, which is taking what I was trying to show you on the previous slide, that the electron can go, whoops, let me get a better color, it's easier to see. The electron can go to this first level, or it can go up to the next level. And actually, if it's on a higher level, it could even pop up to level higher. But eventually, the energy that was used to push the electrons to these higher levels, it's going to basically go to heat, and when it does that, it's going to release light. So it can come from this first level, from the next level, or one of these intermediate levels. When it falls the furthest distance, that's going to be the highest energy, and that's going to produce the shortest wave light, or the blue light. If it's going a shorter distance, that's going to be a lower energy. It's going to result in a longer wavelength, and it's going to give you a color like red. Now, we would have been doing an experiment on this in class if we were having, face-to-face experiments, and I may try to get something together like that. But right now, that's not where we're going to be going on our next experiment. We're going to be doing something that's related to thermodynamics. So I'll stop a second. Has anybody got a question on any of this stuff we were looking at up to this point? You may have seen this before, probably have. Okay, so now we're going to take all this, what we've been talking about with light and the color of light, which is indicative of its energy, which is then related to its frequency and wavelength, and how it can interact with matter. And we're going to move all that into these limited energies that are acceptable, and that is the whole subject of quantum numbers. So where we're going to be at right now is, yeah, Gary. Oh yeah. You can have it into the ultraviolet, and what will happen eventually is you'll get to, okay, certain energies and certain colors of light are going to interact with what's called the valence electrons, we haven't got to yet in class. And then later on, when you get into, say, X-ray energy, it's going to go for the electrons that are not on the outer orbitals of an atom. It's going to be going into the inner orbitals. So you can do experiments called X-ray fluorescence, which helps you figure out the identity of a atom that's in a sample. And then you can also have infrared light, and that interacts with the electrons in a different way. So, but anyway, we're going to be focused mostly on these ones that are for the valence electrons. So anyway, where we're at now is looking at quantum numbers, and we're going to start out with our first quantum number, and it's got the symbol of a italics N. And a rule for what is a legal principal quantum number is it has to be an integer that is greater than 0. So not 0, but it could be 1, 2, 3, 4, things like that. So as we get further from the nucleus of an atom, the electrons are going to have a higher energy level. So we got our first energy level, N equals 1, 2, 3. The reason why you're not going to have N equals 0 is that would mean that the electron has no energy, and that's not really possible. Now, originally, people thought that these energy levels was as if the electron was orbiting around the nucleus, going around it, you know, like the planets. So same thing here. They would have thought it was going around the nucleus. So the nucleus would be like the sun, electrons would be like the planets. Well, they realized that that's not really what's going on, that a more appropriate way to look at it is that the electrons are in a particular space around the nucleus. So at that first N equals 1, they're going to occupy that sphere that you're seeing in this first picture. Most of them are going to be on the surface, though. Most of the electrons will be on the surface of the sphere. There'll be a decreasing number as you get closer to the nucleus. A thing that is very strange, we'll only talk about it for just briefly here because it doesn't really have a practical use, but it's interesting. A atom could have an electron that's actually, say, on the other side of the universe, but yet it is the electron for that particular nucleus. And that gets into something called entanglement. It's more of for the domain of physics, and so we're not going to go there. But the idea is that this location and also which energy level it's at, whether it's at 1 or 2 or 3, is really a probability sort of relationship. Probably the electrons at energy level 1 are on the surface of this sphere, but a few are going to be closer to the nucleus and a few are going to be further out. And as I said a moment ago, a few could be on the other side of the universe. Now, if the N is equal to 2, it's a bigger ball. But you notice the ball has an empty space in the middle where the 1 would fit inside. And then if we're at energy level 3, or N equals 3, then the majority of the electrons are going to be, I'll change colors. Majority of the electrons are going to be on the surface of the air, but they could be further in, but there is a cavity inside where the previous orbital would fit. So what N is telling us is it's going to be the energy. Let me get my texting here. N corresponds to energy. The energy of that electron. Now we're going to go to our next quantum number, and it's going to give us different information than the energy. So our next quantum number is, oops, get the marker going, is angular momentum. It has a symbol of an italics lowercase l, and only certain values are going to be acceptable. It's going to be anything going from 0 up to whatever n was or is minus 1. So if n equals 1, then the only value that L could have would be 0. If n equals 2, then L could be either 0 or 1. And if n equals 3, then L could be 0, 1, or 2. You guys get the idea, I think. We then need to be aware of this particular nomenclature or way of naming the quantum numbers that you need to keep in mind, because it has been around for a long time. It's not going away. And you're going to see it again if you take some more chemistry classes. And that is, if the angular momentum is equal to 0, then we also would say that it is equal to the letter lowercase s. And if it's equal to 1, it's going to be p. So 0, 1, 2, 3 is SPDF. You'll need to memorize that. You're going to need it later on. So you want to go ahead and do that if you haven't already. You may have already done some of this stuff. Now, angular momentum, what that's really telling us is what is the shape of the orbital. What's the shape that it takes. And oops, let me get that bigger. There we go. Yeah. Angular momentum is going to tell you the shape. And we're only really going to worry about 2 of the shapes, because after a certain point, the shapes are so complicated that you're just not going to be able to do it, really. So let me, okay, I'll do this over here. If it is angular momentum is equal to 0, oops, if angular momentum equals 0, or if it's considered to be an s orbital, then the shape is going to be a ball. If, on the other hand, the angular momentum is a 1, or if you're using the letters, it's a p, then it's going to be shaped what they call a dumbbell, where the electrons are out here on either one or the other of these, and there's none in the middle. Now, if you go to angular momentum 2 or 3 or D and F, the shapes start to become very complex. You can see over here what they would look like. This right here would be for the D's, and below that are the shapes for the F. So, those are kind of hard to describe in words. They would pain to try to memorize. You guys aren't going to have a need for that, so we're not going to worry about that. But I do expect you to remember that angular momentum 0 or an s orbital is going to be shaped like a ball, and that if it is angular momentum equals 1, or we consider it to be a p orbital, that its shape is going to be this dumbbell shape. Okay? Now we have another quantum number we have to consider, and that is the magnetic quantum number. Its symbol is a lowercase italics m, and there are certain rules for what it can be. It can be 0 and then positive the value of L, angular momentum, or negative the angular momentum. So for instance, if L equals, let's see, if L equals 0, then magnetic quantum number could only be 0. If L equals 1, then the magnetic could be either negative 1 or 0 or positive 1. And here's what that's doing. This is why this is important, is that the magnetic quantum number gives you the orientation of the orbital. That is, let's consider our p orbital and momentum 1. They've got a picture here at the top that I think helps to show this. We don't actually know what negative 1, 0, and positive 1 correspond to. We just know they're different from each other. But we could sort of say, well, negative 1 could be the case where that dumbbell is going on the x-axis. It's going from left to right. And then we could say, okay, if the magnetic number is 0, then we could put it on the y-axis. So it's up and down. And then what I was about to say a second ago there is we could say, okay, if it's +1, then it could be on the z-axis. It could be going from, say, front to back, like that. And again, we're not going to worry about knowing what these orientations are anything larger than when L equals 1, okay? Because, again, those orientations start to become really difficult to express. If you look at the pictures here for the d orbitals and the f orbitals, it really is sort of just a mathematical concept, or you can use some sophisticated computer program to give you a picture of what it looks like. But it's really pretty difficult, so we're not going to go with that. So has anyone got a question on, I'll go back here a second, on the principal quantum number, the angular momentum quantum number, or the magnetic quantum number? Either raise your hand or chat it or whatever. Okay, then let's go one more slide here. We're going to take all this and we're going to put it together into a table. And what we have in the first column of our table, that's going to be our principal quantum number. So we've got those in this column. And then we have our angular momentum quantum number, L. So you can see that when n is equal to 1, that the only value you can have for L is 0. But if n equals 2, then it could be either 0 or 1. Those are right here. And then if n equals 3, it could be 0, 1, or 2. And if it equals 4, it could be 0, 1, 2, or 3. We already talked about that on the previous slide. And then what they're doing in this next column over is they're converting the angular momentum number to a letter, and then they're combining it with the principal quantum number. So what they're saying here is if the principal quantum number is 1 and the angular momentum is 0, 0 is the same as S. Up here, 0 is the same as S. So we call that a 1s orbital. You see, you can also have a 2s orbital. But when we get into principal quantum number 2, it is now possible to have a value for the angular momentum of 1, which is the same as p. So that now we have a 2p orbital. We're going to do a worksheet on this. Once you've done it some, it's really not all that difficult. Again, we want to remember what the limits are for what we can have for a quantum number. We know that n has to be greater than 0, and it has to be an integer. And then for the angular momentum, it's going to be numbers ranging from 0 to n minus 1. Now our next column over, those are the different values for m. So if you're, I'll change colors because this is going to get busy. If our principal quantum number is 1, the only value we can have for angular momentum is 0, and the possible value of the magnetic quantum number, m, can only be 0 also. If, on the other hand, our principal quantum number is 2, and we're only going to consider if angular momentum, or L, is equal to 1, then we have 3 possibilities for the magnetic quantum number. It can be positive 1, 0, or negative 1. Now, a way to describe what the possible values are is down here, and that is that it can be whatever the value of m is going out, or excuse me, it can be 0 in the middle, and then m can be all the way out to the positive value of L, and then in the negative direction to the negative value of L. Now what we're then going to do here is, well, we need to consider this. I'm gonna erase and start from beginning here. Okay. A set of 3 quantum numbers, 1, 0, and 0, that is 1 orbital. Okay? So to describe an orbital, it is going to require the principal quantum number n, it's going to require the angular momentum L, and it's going to require the magnetic quantum number. In this case, its value is 0. So the quantum numbers here are going to be 1, 0. So that describes a single orbital. Now that's going to be the same thing when we go down here to principal quantum number 2. It doesn't really change anything up. But if we have principal quantum number 2, and then we also have that the angular momentum is now 1, that's going to allow us to have 3 different values for m. So altogether, that's going to describe 3 different orbitals. And you can see how that's going to change when we get into the f orbitals and the p orbitals. Something that we're going to be seeing in just a moment here, but I want to mention it right now, is that an orbital, I think I'll just type it so as to make it easier to see. is that one orbital can contain maximum of 2 electrons. Oops, here we go. So one orbital can contain a maximum of 2 electrons. An orbital can have no electrons, or it can have 1 electron, or it can have 2. Can't have anything else. And what this is all about is trying to figure out where are the electrons going to be. Again, we're going to do a worksheet here in just a minute, and I think that will help to make this clear. There's one more quantum number that we have not talked about yet, and that is the spin quantum number. So this is the last one. And the spin quantum number, its symbol is S. Fortunately, it's easy to remember. And it can only have one of 2 values. It's either going to be a negative 1/2 or it's going to be a positive 1/2. So within one orbital, it could have no electrons, or it could have 1 electron that the spin is either negative 1/2 or positive 1/2, but we don't know which. Or if we have 2 electrons, one of them is going to have to be, oops, get my marker. One of them is going to have to be spin negative 1/2, and the other one is going to have to be positive 1/2. Now, the reason why this whole spin thing is happening is because of the repulsion between electrons. And by having two different possible spins, it helps those electrons, they have a negative charge, it helps them to be away from each other, so as to reduce the effect of the repulsion. So that's why that happens. One's going in one direction, one is going in the other. Okay, so now I want us to go to a worksheet on quantum numbers. I think it will help you guys on doing these. But before we start that worksheet, has anybody got a question? Just either chat it or raise your hand. Okay, I don't see anybody doing either of those. So let's take a look at our worksheet here for a second. Okay, so in our worksheet, we're going to do a couple different things. First off, name the orbitals described by the following quantum numbers. So, in other words, what you're doing is you're converting this into the letters. You're converting the values of the angular momentum part, the L, into the letters, and we're putting those together so as to get the designation of that orbital. So like for this first one, it's 3, angular momentum, or L, is equal to 0. We know that corresponds to an S, and so that would be a 3s orbital. So I gave one away right there. Then in this next set here, you've got it represented using the letters 1s, 3s, 2p, 4d, 5f. You're wanting to deconstruct that into what it would be for if you were going to use the numbers. So this would be, n would be equal to 1, and then since it's 1s, we know that s corresponds to 0. So these first 2 quantum numbers are going to be 1 and 0. And then this next, What are the possible values of m for the following types of orbitals? So you're going to want to take the letters and convert them into numbers. Then using the rule for what m can be, then you could then answer that question. And then for number 4, how many possible orbitals are there if n equals 4 or if n equals 10? This will take a while to figure out. And then how many electrons can inhabit all of the orbitals if n equals 4? Remember, each orbital can contain 0, 1, or 2 electrons. So we're wanting to know what is the maximum number. So we're going to go with 2 electrons per orbital. And then this last question here, let's just not do that one because this takes quite a while and I don't think it's going to be necessary. So we'll skip that one for now. Now there's another sheet to this, and we're not going to do that one right at the moment. We're going to stick to the first page. Okay? And get rid of that. Now, hopefully, you guys were able to print out a copy of these, so you've got a paper copy to work with. If not, you're just going to need to grab a sheet of paper and do that. I'm going to have you set up in groups, so if somebody wants to go use the whiteboard and figure out what they are. Now, remember that the whiteboard goes away. Anything in the room goes away whenever we stop the group. So if you've got something there that maybe you're going to want later, you need to take a screenshot of it or something. Write it down so you got it, because it won't persist after we end the groups. Okay. So let's see if I've got everybody ready to go into a group. And I got a few more folks I need to put you in a group. Just a moment. Okay, looks like we got everybody in a group. So I'm going to go ahead and activate the groups. And I'll set a timer for this first page. Oh, hi, May. So I'll move her into a group too, or also. And so anyway, like I said, I'm going to go ahead and activate the groups now so you guys can be working on this. And I'll give you guys, this will probably take you about 15 minutes to do. So I'll set a timer and then we'll see where we are. So here we go.